I will go ahead and introduce myself. I'm Dr. J.D. Armstrong. I am the Maui Technology and Education and Outreach Specialist here at the University of Hawaii Institute for Astronomy, Haleakala Division. In other words, someone could write a dissertation just on my title. Good to have all you guys here, and I'm not going to speak any more about myself, except for that you guys know that I always have to make some mistakes during the introduction of our speaker. This month's speaker is Dr. Dave Sanders. I've known Dave for a long time, since I was a graduate student over at UH Manoa.
Well, I admitted you, I think. Yeah.
And he's been regretting that decision ever since. So he's been the grad chair over at the Institute for Astronomy. He came to us from Caltech about 20 years ago, he says. And he's an expert in infrared astronomy, and I think is that a good enough summary? All right, well, let's give him a nice Maui welcome.
All right. To hook me up, or?
So yeah, you go ahead and just, if you'll clip that onto your shirt somewhere, and I usually put it on the collar. Yeah.
Is that too close? Well, did you have it off or what?
No, and just put that in a pocket or
pocket.
Yeah, just drop it in your pocket, and that should be good.
Don't know what else is in the pocket. There's a wallet in there. But
yeah, should be good. Pardon?
Am I on?
No.
It's not a speaker system. It's just
right.
For the.
It's for him.
People.
I think
right.
You have to tolerate my voice, and we'll probably. Do we dim the lights or not? I have some pretty pictures, so we might want to do that. No?
Just the front.
Yeah, just the front. That's enough. Yeah, you want to see me, and I want to see you. So, first, before telling you what a pleasure it is to be here, I'll warn you that we're sort of rigged up with a mouse and a pointer, and I may be dodging back and forth to go back and forth on my slides. But I probably predate most of you here, well, with respect to this building and Haleakala. I'm sure some of you have been here on Maui a longer time than I have, but I came here 21 years ago. And I think the last time I was over here, this building was not built yet. And I gave a surreptitious tour to a bunch of folks. And Pan-STARRS was not on the summit yet. ATST was a pipe dream. It's a pleasure for me to be here. I mean, it's an amazing building. You don't know how lucky you are to have this facility at your beck and call. And I'm very happy to join the Speakers Bureau here for what looks like an excellent set of monthly talks. I've been reading finally the website. I had no idea that this is broadcast to the rest of the world, so pardon my nervousness. I'm kidding, of course. And I won't apologize for the title of my talk. It's not a solar talk, but I assume that you're not wedded to the sun, except for life, of course. But there's a lot going on in astronomy other than solar, and there's apparently a lot going on Haleakala other than solar as well. So J.D. mentioned my field is infrared astronomy. It's sort of multi-wavelength astronomy, everything from radio to X-ray. But I sort of started out in the infrared field, drifted into the radio sub-millimeter, millimeter wave field, then back into the infrared. My telescope of choice right now is something called ALMA, the Atacama Large Millimeter Array in Chile, where I was a few months ago at 16,500 feet. You want to talk about being brain dead, that's one place to do it. Everything is oxygenated there. And I should say that array, to give you some history, when I originally came here, we thought that array was going to go on Mauna Kea. And NRAO was going to build it all by themselves, and it was going to, they had a 25-meter telescope slated for one of the peaks there. And so I made my way to Hawaii, expecting that all that was going to come to fruition, and of course none of it did. That was the Jimmy Carter budget cut years. That project died twice and therefore was wiped off the face of the earth to be replaced by a a new concept for the radio. It's sort of like in solar, you have a new telescope, a bigger and better thing to look at the sun. Optical, we have the TMT coming to Mauna Kea. In the millimeter short wavelength radio field, we have something called ALMA. And it's going to be 64 antennas. For those of you who know something about the Smithsonian array on Mauna Kea, that is what ended up on Mauna Kea, and that's a miniature version of what's going on in Chile. 1,000 square meter collecting area, and a partnership of the Europeans, the U.S., the Japanese, everybody else who can buy in. It's a $1.5 billion project, and that seems to be the way big science is these days. Now, I'm giving you that as background so you know something about my history, and I'll weave that into my talk for a moment. I've been interested in galaxies, including our own Milky Way. My thesis project when I was at Stony Brook, actually, I started at Cornell and then ended up having a little hiatus around 1970, Vietnam. When I came back, I went to Stony Brook and ended up with Phil Solomon and Nick Scoville, who's now at Caltech, doing the first survey of our own Milky Way for carbon monoxide, the stuff that comes out of your tailpipe in your car, I guess. That's a molecule that should not exist in space because it would be dissociated by ultraviolet and stuff from hot stars. But what was found was, by Penzias and Wilson, who went on to win the Nobel Prize, of course, for the 3-degree microwave background, what was found was copious amounts of this CO molecule floating around in space, and it seemed that it identified regions of dense molecular gas. For example, if you look up at the Orion Nebula, and you see the stars, the bright stars that make, you don't know that there's 100,000, almost 1 million solar masses of molecules and dust surrounding that entire complex. That's called a giant molecular cloud. That was my thesis. And I discovered about 5,000 of those in the Milky Way. And that was the first time that we had an idea of where all star formation occurs. It occurs inside dense gas regions which self-shield themselves against the UV radiation that would normally tear apart molecules. The dust absorbs the UV, which never penetrates inside the inside of the cloud, and therefore that cloud can sit there. As it gets big enough, gravity pulls it together, and that's what makes stars, clusters and groups of stars. So every constellation you see around the sky has probably been born inside a giant molecular cloud. Anyway, that's my background. How does that translate into colliding galaxies and what have you? You'll see in a moment. Now, let me see if I know how to work this. I always start my talks by reminding you that the news is alive with astronomical discoveries, and I'm sure all of you pay attention and go to the NASA website and read the paper and find out what the latest and greatest is. So I just pointed out two things that actually sort of relate in a peripheral way to what I'm going to talk about. This week's astronomy news, actually from the HST website, is a dark matter news flash. It actually involves a cluster of galaxies which are, when the cluster is actually lensing background galaxies, and that's what gives this shape of stretched out background things. And of course now you know that the amount of mass that it takes to make these lenses is much more than you would add up if you just added up the visible stuff. And so we know there's about 5 times as much as the visible stuff, and that's what's called dark matter. Behaves gravitationally. I point this out because this is an actual image that, it's an image of a region that Harold Ebeling, one of our colleagues at IFA Manoa, has been working on. He defined the MAX project, which is a cluster survey in the X-ray. And then next week, if you don't like dark matter, tune in to hear Brian Schmidt, who just won the Nobel Prize, part of the Schmidt, Rees, and Perlmutter prize for supernovae, and discovering that the universe really is permeated by dark energy in addition to dark matter, whereas dark energy is pushing things apart, sort of like an antimatter. I'm sure I'm wrong in saying that, but dark matter and dark energy are widely featured. So let me get on to the talk. Some background. All of you know about the Milky Way. That's your home. You live your dust debris around your nearby star, G5 star, the sun. Am I right? Is it G5 still? Okay. But there are 100 billion stars, not all like the sun. They all have a range of masses. And they're arranged in a pinwheel. The center of the pinwheel is called the nucleus, and then the rest are spiral arms. But it looks like, if you looked at it edge on, it's like a frisbee. It's not solid. It's stars, but they're held together by their mutual gravity. We're sort of a normal and a largest spiral. There are dwarfs. There are even things bigger than us, but we're at the large end. It's a spiral, and it's got a bunch of letters. It's got a bar now. I played a little role in that with my thesis by mapping out these star-forming regions. Some of my colleagues went a little further and actually determined that rather than a perfect pinwheel, there was a little barred structure in the center of our galaxy. So around 20 years ago, the IAU decided that the proper nomenclature for our galaxy was a SB, spiral bar, and the little c just means that it has something called a spherical region around its center, which isn't perfectly flat, thin like a frisbee, and it's called the bulge, and it's got a small bulge, and that's what the C means. A big bulge would be A, medium size would be B, a little one is C. And in addition to this pinwheel shape of 100 billion stars, sort of concentrated a little bit towards the center, but spread out over a large distance, there's a 3 billion solar mass black hole sitting in the center, in the nucleus. And there's a whole story about how these things were discovered and all the pieces, but that's where you live. That's your home, in my thinking. So we've got the solar system, but then our solar system lives in this thing called the Milky Way. And why it's called the Milky Way, you must know. If you go out on a dark night, certainly in the southern hemisphere, you can see it better. But in the northern hemisphere, I was just up on Mauna Kea. You can go up Haleakala. I think this time of year, probably, I think you can still see a little. No, the galactic center is probably set by the time sunset comes around. But you can still see enough. You're looking towards the center of our Milky Way. You can still see a swath across the sky, which looks sort of milky or white. What that is just 100 billion stars, all packed close together. So, and if you look. So you think of living in a frisbee, and you're looking towards the center of the frisbee. If you look out perpendicular to the frisbee, you don't see that many stars, but you look in towards the center, you see a lot. So you can go look at your Milky Way. You don't quite have an idea of how big it is, but radio astronomers helped us figure out how large it is. The sort of the canonical diameter is something like 15 kiloparsecs. Now, a parsec is 10 to the 7 AU. That's the distance from here to the sun. So 10 million times that, and then take 10,000 times that. And that's the size of our Milky Way. Okay? Well, no. Okay. And those are the units that I'm going to be thinking about. And inside that lies these stars that have already formed, and enough gas to form another billion stars. Okay. And our galaxy is forming on average about 2 stars a year. Okay. But there's enough material right now to form another, 10 to the 9, let me make sure. Yeah, I got to get it right. I tell my students to not confuse millions and billions, but at least, maybe 3 billion more stars. And the fact that, and these molecular clouds could do it, actually. They could collapse and actually form that many stars at the rate of 1,000 stars a year. But For some reason, they don't. Molecular clouds, when they form one star, the star says, oops, I'm going to put some back pressure on the cloud and prevent it from collapsing. And so it's a self-regulated process. So we form stars at a very low rate. But now I'm giving you a lecture like I was in a class. So let me go on real quick. That's what you would get. This was taken by one of our graduate students who's now a Jansky Fellow and a staff member at ASIAA, the Academia Sinica in Taiwan. And he just took this with a wide-angle lens in Taiwan. And that is a picture of your Milky Way. That's the Milky Way. Now, you notice it's got, it's sort of a little bigger here, fatter here, and thinner out towards the ends, and it's got dark streaks running through it. Turns out those dark streaks, which sort of run down the center of it, that's the real center part of the disk. That's where most of the molecular clouds are. And as I mapped with a radio telescope all along here, I just discovered, hundreds and then eventually thousands of these things, measured their sizes and their masses, etc. Okay. The galactic center's right in here. That little C that went around the SBC nomenclature for the Milky Way means that this region is sort of where it puffs up a little bit. If I outlined the Milky Way, it would come down like this, and it would go up like this, and then back down, and then be thin out here again, come back in, and so this center region is what we call the small bulge, okay? And in the center of that is the nucleus with this black hole. Huh?
How do you know where the center is when you look at it? When you look at it?
You don't. And so, but if you went with a radio telescope and all of a sudden, as Carl Jansky did, you point it towards here and there's something that comes booming out at you, and it turns out that now we know it's got little mini jets of radio stuff. It can be located in the radio. And that's a very good question because now in the infrared, not only has the center been seen, but and I'm sure he's hoping for a Nobel Prize in this too, that they've actually measured stars whipping around this central black hole. And there's a little movie, and it's the one movie that I have the picture of the movie, but I lost the movie, so you can't see it run. But you can go on the web and actually watch a time-lapse movie of stars orbiting this black hole in the galactic center. So they actually know its mass very well now and its location. But it was always suspected the pinpointing was where this powerful radio source was. And then the proof that it was a 3 million solar mass black hole was due to the, Kepler's laws and watching the stars rotate around it. It's an excellent experiment. Yeah.
Those dust clouds, how much light are they actually blocking that we're not really seeing?
Well, great question. It's sort of like the light that you see here should be sort of uniform across there. Yeah. Remember, that light is, that's a million stars beaming at you. And when you're looking out here and out here, you're seeing your nearby neighborhood. Okay? When you look that way, you're looking into the Frisbee towards the thin disk. Okay? But so I say to my class when I'm teaching, I tell them about this, show them this picture, and then try to have them, I say, forget that. Just imagine yourself, remove yourself from the Milky Way, put yourself on another galaxy looking in, and then I will tell you what we look like, and I will show you pictures of what we look like, and then you can try to reverse the process, being inside a galaxy and imagining what it would look like, across your sky.
So we're looking across from an arm.
Well, you'll see. Just a moment. Perfect. Well, there's the view from Earth. That's another sort of blown up view. The other was the student's picture. This is a sort of I think, a combined infrared optical view showing a little more detail. The thing is not running this way, but of course it's running this way. It doesn't matter. So here's the cartoon. This is the pinwheel of stars, and you're right. What you were saying, the sun is out here we're on the boondocks of the galaxy. We're debris around the star, and the star is sort of at the edge of the Milky Way, and, it makes you feel a little unimportant, but never mind. At least we can think. Here's the kiloparsec. When I said 15 kiloparsecs, I took the 8 and multiplied by 2 to get a sort of a diameter. Then I expanded a little bit to capture all the visible light. These molecular clouds that I was talking about are dotted. They would be about the size of this green pointer. And there are about 10,000 of them sprinkled throughout the galaxy. Okay? And the bright patches you see here are clusters of young stars and massive stars that have formed inside a molecular cloud. And so now, the whole region here is populated by old stars that are fairly dim, like the sun, and they sit in this thin disk, and they all rotate. And the reason it's a spiral is because it's not solid. The inner parts rotate faster than the outer parts, so it winds itself up in the inside, and the arms on the outside become arms because they're trailing. You know, there's no stick between here and here that says when I rotate like this, you've got to come along with me. It says, yes, you have to come along, but by gravity, and it takes you a while, and okay, you follow it. So it takes us 200 million years to go once around the Milky Way out here. Inside here, it might only take 40 million years to go around once. Anyway, that's a picture of our Milky Way. The nucleus, the bulge in here, the 3 million solar mass black hole here, the billion solar masses of molecular clouds out here to form more young stars, and 100 billion stars in this thing. So do all galaxies look like this? Well, most spirals do. Yes? Yeah?
If you're looking down at that galaxy,
this?
Is it rotating clockwise or counterclockwise?
It's good. Actually, this one's rotating like that. So it's trailing arms, so it's rotating clockwise. That's a good point. Yeah.
How many times has our sun gone around the...
Excellent, excellent. Our sun is 5 billion years old. So it takes us 200 million years out at this distance from the center. It's just a Kepler's law again to go around once. So that's 5 orbits per billion years. 5 billion years old, we've gone around 25 times. Excellent point. And we've drifted away from the original molecular cloud we were formed in, because once we form, we decouple from that cloud. The cloud stays together because it's little gas particles that hit each other and bounce and such, and so they can't get away from each other. Once the sun forms, it doesn't really interact anymore with its surrounding gas cloud, and it can basically drift away. But yeah, excellent questions. I wish my class would speak up that well.
Dr. Dave, before you flip it, I was going to ask you, around that center core.
Yeah. See, now I have to go back.
They seem like they have a much more bluish tint.
Sure. They're excellent. This is an artist picture, by the way. Yeah. So, but if it were more blue in here, you'd either have to say less dust obscuring it, but probably more young massive stars, what we call OB stars. Yeah, bluish. Well, young stars. Blue is from young stars, where they still emit a lot of ultraviolet. The old stars are sort of yellowish, like the sun. That's why your eyes are tuned to 5,500 angstroms, whatever. Anyway, let me go on. If you really wanted to peer into the galactic center, this is in the near infrared where we can actually penetrate through some of the dust. And you see how close packed. This is an actual infrared image with a high-resolution camera. Instead of kiloparsecs, now you're looking at 5 parsecs. So it's like a size, smaller than my green dot on the previous picture of the cartoon of the Milky Way. So it's a very dense, packed group of stars. And if I go on, if you really look in, now I'm getting close to the galactic center, and you see things puffed up as big stars. Big stars. Well, yes, massive stars. And the next thing, well, when I first taught my class, I had just been here a year. I came in '89, so I've been here actually 22 years. I taught my class, and I usually pull things out of the newspaper for them to read. And at that time, that was the first inkling that we might have found a black hole in the center of our Milky Way. And, of course, this made it into the Sunday Honolulu, I guess it was Advertiser at that time. And you can read well, you can't read. But anyway, it captures the public imagination. That was 21 years ago. Now, of course, now we've actually measured its mass. We know it's there. And if this movie actually worked, I wish I could double-click and have it work, but you would actually see these numbered stars orbiting in ellipses around this point, which is the galactic center. And from the period of their orbits and the size of the semi-major axis of the ellipse, you can actually compute the mass of the central point. And that diameter is 10 light days, which is, well, it's a pretty small region. Anyway, it's quite remarkable. But let me back up now, and I have to start moving a lot quicker. But you've had enough about sort of what our Milky Way looks like, what it's composed of. Charles Messier, whom you should mostly know that name, most of you should know that name. Actually, his probably great-grandson taught at Iolani here for a while. Actually, when my son was there taking classes. That's just an aside. He wasn't teaching astronomy. He was teaching physics. And he's no longer there. He was there for 5 years, and he's gone. But his great-great-great-great-great-grandfather set out to actually catalog objects in the sky which he didn't want to be mistaken for comets. And so he was trying to get rid of all of the fixed things that didn't move. And so he made a catalog of 100 of these brightest things in the sky, and they turn out now to be a mixture of things. This is what he called fuzzy objects. He actually, I think, the final catalog has 113 objects, something like that. Huh?
110.
Oh, Jesus. Wow. It's amazing. Thank you. Thank you. Actually, I trust you. Yes. I knew it was more than 100, but why I thought 113. I bought the book, and you're probably right, 110. You know what M1 is?
Crab Nebula.
The Crab Nebula, yeah. So there are a variety of things. There are a lot of exploded stars. There are a lot of galaxies in the Messier catalog. They were things that were extended, and he just wanted to make sure that if you go out on another night and you see that same thing, that's not a comet. You just subtract off all the Messier objects and then look for other stuff that moves. Okay, and they're known by their M numbers. Okay. And some background about galaxy types. Just the Messier thing discovered a lot of galaxies. But after Messier, there were bigger telescopes. People started measuring extragalactic nebulae. It took them a while to figure out that they were really not part of our own galaxy, because some of the Messier objects are star-forming regions in our own galaxy, about a third of them, maybe more than a third, actually. So there was 100 years or more, or 200 years of cataloging all these nebulae. And what do you do when you first discover something? You make you invent names, A, B, C, 1, 2, 3. You give them names and numbers and then locations in the sky. And galaxies were known by their shapes. They were either elliptical or these spiral pinwheel things. These are sort of called normal galaxies, and there's tons of them. The Milky Way is one. Most of the galaxies nearby us are actually spirals. Well, that's not quite true, but they're smallish. There's one of Messier's spiral nebulae. It's amazing at the time that he really didn't know whether this was another galaxy like the Milky Way or whether it was just a star-forming region in our own galaxy. But if it was a star-forming region in our own galaxy, it had an awful lot of symmetry to it. Star formation might be a messy process. Why would you have a pinwheel-shaped thing in our own galaxy-forming stars, especially when you look up at the sky and see this band, the Milky Way, running around, and you try to figure out what you might be living in, and then you see some things like this, and you see a few other objects. When this is edge on, you can sort of see, your brain can start piecing things together. What if you lived on the edge of one of these things and looked in? That's how one figured how, well, you get the picture.
Pretty obvious that the Earth goes around the sun round too.
Yeah.
It wasn't obvious. Just
Well, that's a disk. Yeah.
pretty obvious now.
Yeah. No. It takes 30 years, 40. It takes a few generations, enough data, and seeing things like this. Okay. So that's the face-on version. Here's the edge-on version. Okay. Now you can imagine living out here and then, looking up at the sky. You look out this way, you just see a few stars. You look into it, you can see a sort of a swath. Anyway, it's hard for me to transform the room into a into a planetarium. There are dots around this. We now know these to be globular clusters. This is a pretty good analog of the Milky Way. That's the small bulge in the center, the little C. This is the thin disk. A lot of dust here, which is absorbing the starlight. That's equivalent to those bands that run through the center swath of the Milky Way. Anyway. And we've found out, since 200 years of cataloging things like those nebulae, and our own Brent Tully, who's here and cataloged the nearby universe for us. He didn't discover the local group of galaxies, but he's certainly done a lot to measure the environs of our local group. We now know that we live, I cut this out of a little textbook somewhere, and this is meant for a class, not so much for you, but it gives you size scales here, and it has little cartoons for our Milky Way, a spiral here, and we're surrounded by the Large Magellanic Cloud, the Small Magellanic Cloud, Leo 1, Leo 2, Carina, Fornax, Sculptor, Ursa Major. These are all either dwarf ellipticals or dwarf spirals. NGC, the new general catalog, as I said, 200 years of cataloging. They started giving, different catalog names to objects. The 6,822nd object in the NGC catalog. And then out here, about 670 kiloparsecs. Remember, the diameter of the Milky Way is about, if you really go out to the edges, is sort of like 15 to 20 kiloparsecs. And remember, the parsec is 10 million AU. Okay. So there's the Milky Way, and it's surrounded by its little menagerie of smallish galaxies. And then over here is this thing called Messier 31, which you now know. You know the name of Messier 31? The Andromeda. Wow. Yes. Also surrounded by smallish things, M32, NGC 205, Andromeda 1, 2, M33 is in here, NGC 1. Anyway, a little group of galaxies here, a group here. And we refer to this whole thing as the local group. There are about 24 members, dominated by two large spirals and a bunch of smallish spirals and dwarf ellipticals. We call them dwarfs because they're small. How did this come into being? And what's going to happen to it in 5 billion years? That's my talk. Well, that's a close-up picture of Andromeda. I don't think you can quite get this with your small lens and backyard camera, but you can probably get a picture. I don't know. Can Falks get a picture that is this good?
It's too large.
Okay, but it can start to resolve stars and such, and then not stars, but resolve parts of Andromeda. Okay, but this, of course, is I don't know whether this is a Palomar image or a Hubble image. It's probably a Palomar image. Okay. It isn't, because it was taken before Pan-STARRS was built, but it could be a Pan-STARRS image. You're right. These are the two satellite galaxies floating, orbiting Andromeda. You notice that, I have to tell you, there's actually a warp in this disk, and the only way one can generate a warp like that is presumably if one of these little companions plunges through the disk, and that will do it. So I'm going to just jump ahead and tell you that there's been a lot of cannibalism going on in our local group and with all galaxies in general. As stars are born inside clusters, galaxies are also born inside clusters from larger clouds of gas and dust that fragments and under gravity forms a galaxy, which then, like all gravitationally bound things do, they form a rotating disk, thin disk. But not everything ends up in a single rotating disk. You get a whole bunch of things and a whole size spectrum of things. And what determines that size spectrum is the amount of material, the amount of gravitational force, et cetera, the density. And so we can sort of work our way backwards into what it was that condensed to form our entire local group. We know it made two big spirals. I think simulations now tell us that we probably had 100 times more dwarf galaxies flying around like little, flies. And the large galaxies have basically been accreting them, eating them. And we're now left with sort of 20, 10 largest dwarfish members of each large spiral.
Yeah. Feel for the size differentiation between these galaxies. So are Andromeda and Milky Way represent?
Andromeda and Milky Way are about the same. Great question. Huh?
How big are the small ones in a percentage?
Well, that's a good point. My guess is they're sort of like 1% of the mass of these two. Yeah. I think I'm...
Totaled up?
Totaled up, it's like the sun and the planets. The planets are basically 1% of or less of the sun's. That's a great question, but that's it. Now, I'm not saying it was always that way. I mean, the initial collapse may have had things that were sort of tenth the size of the Milky Way, and those tenth things then quickly coalesced into one of these. So I don't know that history, although that's being worked out. Of course, it's being worked out now with not just visible matter, but with dark matter as well. You put that in. As a matter of fact, that's one of the reasons we know there's dark matter. You need that in order to get the clumping of the way it was done. Of course, now we can measure dark matter directly by looking at how it makes arcs, and lenses. Anyway, that's our neighbor Andromeda. We know it has satellite galaxies, but it's also been eating galaxies in the past, we think, because we know that these things plunge through the disk. Actually, if you did a map of atomic hydrogen around with a radio telescope around the entire local group, you would see streams of gas that actually trace the orbits of these little things as they sort of swing around the galaxies. They leave streamers and they pull out tidal arms and such, and you can see the whole history of that, of the interaction.
Yeah. They obviously leave some of their material with the host.
Oh, they do.
But they continue on.
Excellent question. And sometimes, if they get on the right decaying orbit, they just get eaten alive, and their stars basically merge with the galaxy. The reason we know that that's happened in the past is those orbits get scrambled for the little guys, and sometimes they can actually be going the opposite way around the galaxy from the galaxy's rotation, so that when they get accreted or when they get eaten, their stars, which don't collide with the stars of the galaxy, are going the opposite way. We call them moving groups, and they've been discovered, around, mixed in with our galaxy's stars, and so we can trace the past history of these minor merger events. Yeah, great question. Anyway, I show this to my class too. I hate this picture. It's sexist. It's got everything going wrong for it. That's Hubble with his pipe. No one smokes a pipe. No one looks through an eyepiece anymore, although you could, I guess. And that's the Mount Wilson telescope. It's the one he used. In the 1900s, I think he made hay during World War I when L.A. was blacked out and he had the dark skies all to himself. He discovered the law of expansion, or the redshifts, or whatever you want to call it, the expanding universe. But I did it simply because of the name Hubble. Spirals, we now know spirals and ellipticals, as I said, two types of galaxies. I haven't really shown you an elliptical yet, but it's a puffed up bulge. Just take that little bulge in the center of the Milky Way and just make that a big football thing and get rid of the disk in the middle. Ergo, an elliptical. Ellipticals have very little gas and dust. What it really is matter of fact, you could, well, I'm giving the punchline away. I cannot tell you. So, again, this is a zoo, and then there are things called irregulars that don't fit either a spiral. And the irregulars are mostly smallish things that don't have enough gravity to organize themselves into a nice thin disk, and they constantly get perturbed through interactions with their neighbors, and they just look like a rat's nest. And these three galaxy types, all galaxies seem to fit into these types, and they can be big or small, fell into a normal and an active category. I've only told you about the normals so far, but the actives turn out to be things where that black hole in the center starts acting up and showing itself. We now know that that black hole, if it's big enough, can outshine an entire galaxy on its own, not through nuclear processes inside stars, but through accretion onto black hole, where E mc squared, you actually get a tenth of the rest frame mass out in terms of E&M energy. Yes?
Yeah, that was my question.
Yeah.
I'd seen that movie.
That's an active.
I had seen that movie
What?
That you had showed earlier.
Yes.
Where the couple went
Yeah.
going around.
Yeah.
We have not been able to actually watch it eat a star yet, have we?
No.
We have not
No.
seen it.
Although there's been speculation when there's a little flare of radio energy or something from our beast in our galactic center, there's the thinking that something has fallen in. Probably not a star, but some clump of gas has fallen in. But if our black hole were being fed ravenously, or eating ravenously, it would turn our galaxy into an active galaxy. So we have a massive black hole. We now know all galaxies have a black hole in their center of varying mass. Apparently about 0.1% of the mass of the galaxy is always sitting in a black hole in the center. I'll tell you a little more how that gets there. And when it flares up, when it acts up, it eats a lot, you classify the thing as an active galaxy. Okay, anyone who's ever read a fairy tale book of elementary astronomy has probably seen this galaxy tuning fork diagram that Hubble supposedly made up. Ellipticals look roundish, but they can either be perfectly round or sort of footballish, and they give a number depending upon how oblate or it is. Spirals, depending upon the amount of winding up of the arms and whether it has a bar or not. And you have this nice little diagram. And supposedly, I guess the reason why it's linked together is maybe these things are all related to some sort of life and death process of galaxies, or maybe spirals turn into ellipticals or bards. It can go back and forth between, or why does one care? But the point is you'd like to understand where all this structure comes from.
So we're in SBC, right?
Huh?
Where's the big barred one?
We're here. Our galaxy supposedly looks like this, although now that I look at this, I don't think it does. Sorry? Was I answering a question?
Yeah.
Yeah.
I don't think it would look like that, but I'm not.
That's a good point. Well, I'm saying this is a cartoon, and so, wow. Yeah, I should go talk to the IAU when they voted that our galaxy was a barred SBC. Okay. That's how it's done. It's done by vote. Matter of fact, our galaxy has changed. It grew, and then somebody had an epiphany, and it shrank again. So, and it was done in consecutive. But by the way, the IAU is coming here in 2015. Honolulu will be at the center of the universe in 2015. The IFA is going to have a series of major lectures. Maybe we can hook Maui into the venue as well, where we're going to have maybe 3 major events a year leading up to the IAU, highlighting different areas of astronomy, everything from cinematography to the astronauts to actual discovery and such. So the IAU votes on things like this, and they've made your galaxy 20% heavier and then 20% lighter, and I don't know what the heck they're doing in here, but at the moment they say we're an SBC.
Yeah, because that was my question. I was looking at that, and I figured we're probably in between on the top, the SB, those two.
Remember, that was an artist's conception.
Right.
No one's ever taken a snapshot on the outside, although we have measured our galaxy edge-on. The IRAS satellite got a picture that was very close to that edge-on spiral that you saw. That's a real picture made. And you can see the outline of the thin disk and the bulge, just the counting the stars. So that actually has been done. But I'm going to get to telling you where we're going to be in 5 billion years. You thought you had a hard time when the sun explodes or puffs up to a red giant. We will actually live inside the sun in 5 billion years. But you will. I mean, this isn't. I always remind people, this is not, Hollywood fake. You don't have to go out and see a movie. You don't have to pretend. This is going to happen. Just think for a moment. 5 billion years' time, you may not be in this form. You will be in, your remnant of you will be living inside the sun. But our galaxy will have done something else. It will have changed its form, and that's what my talk is about. And it will all occur about 5 billion years from now.
So we're halfway there.
That's a good point. In terms of the life of the sun, yes. Well, back to those active galaxies. Hubble made up his catalog of spiral nebulae, edge-on, face-on, big, small, elliptical spiral. Meanwhile, another fellow at what we call Santa Barbara Street, the Carnegie Institution of Washington's West Coast operation in Pasadena, that's located on Santa Barbara Street, had a staff member, Halton Arp, a patrician sort of fellow, always wore a coat, actually looked sort of like Hubble. Now resides at Garching at the European Southern Observatory headquarters in Germany. And he made up what I think Vera Rubin referred to as a coffee table book, which is a book full of fascinating pictures of things that aren't normal. And he published a atlas of peculiar galaxies. And he was excited, as all people seem to be when they see these images. Do you know what was voted to be the most popular image on the Hubble archive? If you go to HST, the Hubble Telescope archive.
Birth of a new star.
Huh?
Orion.
No.
Deep field?
No. It was two interacting galaxies. It was one of the ARP, I think ARP 167 or something like that. That was chosen by you, the public, as being the most exciting looking image on the Hubble archive. I mean, I don't argue with public opinion. So one of Halton Arp's objects was singled out. Okay, this is 1965. I arrived at Caltech in 1984. Arp had already left in a huff after Santa Barbara Street had a falling out with Caltech over who owned the summit, and Arp was no longer given time to go and just take pictures on his own. He had to, there was competitive time, et cetera. And so, anyway, that's another story. This is one of the objects in the ARP Atlas. And this has an NGC number, and it actually has a common name called the Mice. Now, you look at that. What is that? That's not a single galaxy. Matter of fact, when Arp saw this, I think he and Ambart Sumian, another famous Armenian astronomer at the time, member of the Soviet Academy, these were jets coming out. These were being shot out of the center of the galaxy, and something else was... And this thing had bifurcated. It had been a galaxy that sort of exploded and split itself in two. And you were looking at the remnants of the explosion, and this is part of the jet that came out from the explosion that separated the two galaxies. Why it was called the Mice, I don't know. But
looks like it's coming back in on itself.
well, but anyway, that's another little face-on dwarf spiral over here, or maybe a more distant spiral, could be the same size. But this new camera, the advanced camera for surveys that actually took this picture, the previous camera, WIFPIC it was called, took the famous Hubble Deep Field picture, out of which Adam Rees made his great discovery, which led to one of the distant supernovae, which led to the Nobel Prize. That deep field, when they made a new camera, which was actually much bigger and made a bigger single image of the sky in one exposure, and they tried to have a publicity shot of the deep field, it just looked like a whole bunch of small dots and points. And the PI, the principal investigator of the camera, said, "My God, the public is not going to think very much of my camera. It looks like the same, collection of stars that were in the original Hubble Deep Field. Can we do something to it?" And then someone told him, "Hey, go take an image of the mice and show that to the public." And that's what he did. And that's what this image is from. It's from one of the first ACS camera displays. Okay. Now, JD gave me this, and I slipped it in. This was taken with a Faulkes telescope of the same, I mean, it's not quite the same detail as you see in the other image, but this is actually a wider field of view, and it shows you that long, quote, jet that's coming out here. And there's actually, if ARP had seen this, that must be a counter jet that sort of curves off this way. And then there's a bridge between the two, and there's all sorts of other stuff. Okay, I guess you could call that the head of the mouse and the tail or something, but anyway, it was called the mice. So that's what it looks like. A very nice image with the Faulkes telescope. seeing is not as good as HST, so you can't resolve all the detail in the centers of the galaxy. That's another image that's also ARP 244. This is taken with Fawkes. I'll skip past this, actually. This was also taken with Fawkes, and so not just two galaxies. Here's a little Stephan's quintet of galaxies. Some of them also have these tails and what have you. This one has, I think that's an artifact of the lens. But this is just a small group, maybe like our local group of 5 large galaxies. There's 1, 2, 3, 4. I'm not sure where the 5th one is. It's probably here. But these two actually look like they're doing something like the mice are doing. Well, look at this one. That's a splatter diagram if I ever saw one. But what is this? It's also in ARP's atlas. Okay? Pinwheels, bright stars around here. It doesn't look like a spiral to me or an elliptical, but it's something going on. Okay, well, that's what ARP did. If you look in the back of his atlas, it's great to go back and read this now because it's like taxonomy. Well, I got spiral galaxies and double galaxies and E-like galaxies and connected arms and interacting arms and info and attraction groups, chains, wind effects, long filaments, narrow countertails. Anyway, a lot of stuff that was not normal. Well, about that time, 1972, ARP's atlas came out in 65. A mathematician, Allard Toumare, his brother, we call him the big and the little Toumare. Jury is a lot smaller than Allard. Jury actually works at Gila in Colorado. I think Allard is still at MIT. They published a famous paper called Galactic Bridges and Tails, and what they showed was that, and I remember Allard telling me how he did this. He did this with a little kitchen computer that he plugged in 1,000 particles that would gravitationally interact, and he let them evolve in time, and he made 2 spiral galaxies out of 500 particles each, let them rotate, and then he saw what would happen as they passed by each other. They created bridges and tails. We now know, and he did this with a little, he would let it run for a week, his code, and he would look at the printout, on paper, and then he tried to plot pictures of it. So it was his desktop n-body numerical simulations, 1,000 particles. And he was trying to simulate to see whether he could create things like that were in the ARP atlas, and he found he could create them in spades. So we now know that ARP had it exactly backwards. These were not things that were exploding and fissioning. These were 2 objects trying to come together, and as they passed by each other, they ripped off their outer parts into long tails or streamers that would eventually curve and then fall back. And that the 2 galaxies were really interacting, and if they were on a merger course, they would eventually, pass by, then come back, and then slowly settle down, etc. And this is what, this is what Allard did on his printouts. He took 2 interacting galaxies and eventually produced these long tails that would come out of the ends. Okay. Josh Barnes, of course, ran into Allard when Josh was at Princeton and Allard was coming down and actually developed tree codes, which are branching codes, the way you program a computer, of millions of star particles. And now we've gone up to billions, and they've done accurate simulations, and that's the game that's being played all over. So if you actually look at, see if I can click on this. Here's the mice. So Josh spent a lot of his early years trying to simulate exactly the structure, not just, getting it piecemeal, but to do it exactly. And what he did is I think his father had been a filmmaker. And so he was one of the first users with Lars Hernquist and Pete Hutt of the supercomputers in San Diego and Pittsburgh. And they produced simulations running tree codes with millions of particles, hundreds of millions of particles, and then took snapshots of the simulation as it evolved. And that's what you were seeing in that time step here. And that's what this object looks like, caught somewhere in the middle of the act when the 2 parent disks have overlapped and they've left around these tidal tails, and they actually got a streamer. And of course, when you've got it in the computer, you can rotate it as well. Do all of that, and then you can get it to line up exactly. Well, you have to invert this to get that, but sort of. So that's what he spent, before he came here, this is what he was doing.
So there's no escape.
Hmm?
There's no escape. They'll eventually coalesce.
That's right. If they're big enough and close enough, and their velocities are not so large that they're just going to whip by and never come back, yes, then they're caught in an eternal dance. So to get to the end of my talk, what do you think is going to happen in 5 billion years with us and Andromeda? We are in that dance. Okay? This is what's going to happen. You're going to go through all these stages. Yes?
Surely when two galaxies collide, given accelerations and so
Yeah.
on, I'm a little worried. Maybe
Yeah.
it's 5 billion years in the future I'm worried.
Yeah.
Some of the bits of the edges are going to have a whip-like effect, and they're going to be accelerated too fast. Isn't it possible that we might just go...
There, you have asked the same question that someone asked after a similar talk I gave him in Noah. Yeah, are we going to get thrown out of... It's possible. It is possible.
Anybody want to buy a house?
It is possible.
How long does this take for it to go back and forth and finally form again? You know.
This whole process here, there were actually time steps that are up here, I think, that are in hundreds of millions of years. So Andromeda and us are fairly far apart now, about 20 galaxy diameters or 15 galaxy diameters, and we are falling towards each other now. So in another billion years, we will sort of be passing by, and another 2 billion years, we'll be coming back again for a closer marriage. 3 billion years, we'll probably be in this phase. And in 5 billion years, you're going to see where I'm heading here. So we'll get there. Now, what I encourage Josh and Lars to do is put gas in their simulations, because with the stars, they don't actually collide. They don't hit each other. They feel each other's gravity, but they just reshuffle themselves. So when the two galaxies merge, you get a collection of the stars that haven't hit each other. Okay. What about the gas clouds, the gas that's in the spiral disk? Those things do collide. And when they collide, they lose their angular momentum, and they actually fall to the center. Can you hear how the black holes get built? That's how the gas gets pushed into the center in very large quantities. Matter of fact, the billion solar masses of gas that's currently in our disk, 50% of it will get swept into the nuclear region through a process like this in both our galaxy and Andromeda. So our black hole, instead of being 3 million solar masses, will have 2 billion solar masses of gas dumped on it, approximately 5% of which probably will go into building the black hole. So our black hole will grow from 10 to a million solar masses to 1 billion solar masses. And I'll get to the punchline, our stars will end up being distributed in an elliptical shape, because the collision is not planar all the time. It's at angles, and so stars get kicked into, 3D circular orbits, not just in the same plane. And so when the process is through, you have a more roundish distribution of stars and gas which has been funneled into the center. So I could almost stop here, but I'm going to rush through the end now that you already know the story. This is just the gas that's in the two colliding galaxies. I asked Josh to just do he's treated now. These are each individual giant molecular clouds of gas that actually are colliding with each other, and they're sinking into the center. The stars are some big thing out here that are not being shown, and this is just sort of a cute picture. What you see is a very dense buildup in here. It also makes a spiral pattern of the gas and the dust. You get a mini spiral in the center. Meanwhile, the galaxies are out here doing their thing. Yeah, you get all sorts of stuff going on. It's fantastic. What they first showed is that you can dump almost all the gas into the center. This is what makes a luminous infrared galaxy. This is my business. It's what I do for a living. When I discovered these things in the IRAS survey, we wondered what the heck they were. We now know that they're all merging galaxies. If you look at that antenna galaxy, that Fawkes picture that I showed you before, which is underneath here, it's the Hubble picture, overlaid on top of here are all of the giant molecular clouds. This is a map of carbon monoxide. This is a map of radiocontinuum emission. This is a map of infrared emission. This is a galaxy sort of somewhere in between this phase of colliding. The two nuclei are still distinct. The gas is spread all over the place. The disks are getting messed up. If you pulled back and looked at a wide field view of this, you see the big spiral arms coming out this way. This is X-ray emission in the center. It's a multi-wavelength view of the whole process that we've just started to compile. If you actually want to look at what the end product looks like of that previous system, see if I can show it here, this is what it will probably look like. It's a fully merged galaxy with the faint tidal tails falling away. This is called Markarian 231. This galaxy has 500 times the luminosity of our own Milky Way galaxy, and almost all of that comes out from a region which is the size or smaller than my green laser pointer from the center. This is an elliptical. This is what we will look like when we merge with Andromeda if we're looking at us from afar. Okay, our tidal tails will be, hopefully the sun will be in one of these tails, or maybe it will have been brought into the center and hopefully not dislodged out here somewhere. This is that billion solar masses of molecular gas that was normally out here in the disk and has been funneled into the center of that dot. We've actually measured it. This is what ALMA will allow me to do. The ALMA antenna will allow me to resolve this central complex. This is CO in the center. Resolve it on a scale 1/10 the size of my green laser dot there. And I'll be able to see whether that has a mini spiral structure, whether all the luminosity is actually, we think, is actually coming out from the very center of that. That's where this building black hole is.
So it turns into like a globular cluster, just a cluster of stars.
A very big one, but all that stuff ends up, most of it ends up into the black hole. Let me see if I can start this. This is a little cartoon where Josh tried to actually simulate, here you go, and you get the spiral arms, the stuff being thrown around. Now you zoom in to the very center where that billion solar masses of gas is. Here's the artist's conception. Because remember, the two galaxies, the Milky Way already has a 3 million solar mass black hole. Presumably Andromeda does as well. These are the accretion disks or gas around those black holes. And you can actually trace the merger of those black holes, while it's also accreting this billion solar masses of gas around it. Well, that's just a funny thing. And these are gravity waves that get sent out afterwards. And of course, if we're ever to measure gravitons, one of the is a space mission that we're trying to fly internationally that would actually detect the gravitational waves. And one of the chief candidates looking at are these merging galaxies, like the Milky Way. Oh, is that the same thing? Sorry. Let's move on. Okay.
We'll look at it again.
This whole thing can be put in a picture that a theorist friend of ours has done. You start out with an isolated disk. You can have small groups of objects. You start the interaction merger. You get coalescence. Eventually the black hole turns on in the center, blows out the remaining gas and dust that's in the center. You turn into a quasar. And that dies down, and you're left with a dead elliptical. So in 5 billion years, the Milky Way will transform from a spiral to an elliptical. The black hole will go from 1 million to 1 billion solar masses. You'll go through a quasar phase. And, of course, you'll be long dead and living inside the sun. Yes? And that's supposed to be a good thing to think about.
I'm trying to grasp, 5 billion years
Uh-huh.
into the future.
Yeah? Mm-hmm.
So this might sound
Take it a day at a time.
Right.
Yeah.
This might sound a little bit naive, but is this calculated by math? Is this all
Yeah.
math?
Yes.
Mathematics?
Yes.
It's basically mathematics.
Yeah.
So we can't see 5 billion years into the
No,
future.
no. But you know the orbits, you know the masses, you know everything. So you just let the computer run. Yeah.
Okay.
You can't escape it.
Plug in the variables and
Huh?
does it? You just
Yeah.
plug in the variables.
And we can see other places in the universe where this process has carried itself right through. And we're witnessing that, in these galaxies that I started looking at because they were very luminous in the infrared, meaning they had a lot of energy coming out from regions which are heavily shrouded in dust. Now I know that those are these buildups of large amounts of gas and dust in the center of interacting merging galaxies, because I've taken images of all my objects, and they are things that are in the ARP Atlas, yes.
So eventually, I mean,
And this is that picture.
Our black hole will shoot out the plasma.
Yeah, so 5 billion years from now, if you were to look up at the sky, well, that's where I'm going. Let me go on. Well, this just shows that people, if you read papers, I'm sure you won't, but if you do, you'll see terms like gadget, sunrise, cart, ART2. These are all new tree code simulations that are built on Josh's models, where they incorporate gas and dust and dark matter. And we're going to have powerful new instruments that allow us to look from the radio to the X-rays. HST Spitzer was an infrared telescope. Herschel has another year of its lifetime. These are two infrared telescopes that I have used heavily. Chandra is an X-ray observatory. Galax is a UV observatory. We have ALMA, this array in Chile to look at the molecular gas. We have the James Webb, hopefully, which will replace HST if they ever get their cost overruns under control. And then the 30-meter telescope, which we hope comes to Mauna Kea, and will allow us to see on scales of giant molecular clouds in all of these nearby interacting galaxies. That's what you have to look forward, starting from now to the next 10 years. So this is a quick picture of the galaxies that I had cataloged 10 years ago, and now we've taken Space Telescope. As you can see, they're all sort of, this one isn't, but these things from here on out are sort of interacting, merging type systems. You can see that this is sort of like what ARP did. These objects here all have been given weird names. Blue compact galaxies, extremely red objects, Lyman break K plus A, E plus A, Lyman alpha nuclear starburst, scubas. I don't know. It's a zoo. What we finally are doing is unifying this entire zoo and active galaxies, quasars, radio Seyfarts. These are just different forms of eruption of that black hole in the center. And these are close-up pictures. You can download these from the web. They were taken by my student. He led the team, Aaron Evans. But we have I think it was one of our images that was picked as the most exciting image of the year for Hubble. It was either this one or something like this.
Where do we find this?
Go to the Hubble website and look under the Hubble Heritage archive, I think, and Hubble is devoting time, real time, to either take deeper images of single targets or to take them in special filters and process them, and they've set that aside as a special project. And you can go and download wallpaper, cosmic wallpaper, or individual things like this, and it's very high resolution, so you can blow it up and put it on the side of your house if you wanted to, and you'd see every detail. In this case, we looked at 88 objects, and they actually made a big fold-out and sent it out as their annual Christmas present with their annual thing.
Do you think any of this stuff has been added into the Google Sky?
I'm sure it has, because if you know what Google Sky does. When you tap on something and then start to zoom in on it, you basically it goes into a lookup table and starts pulling up the best image it can of an object. So they'll start out with a low resolution thing, and then they'll move in. Probably Pan-STARRS stuff is going to make it into, Google Sky eventually. But I know Sloan survey data has. And finally, this is the Hubble Deep Field picture, if you remember, that was taken in 1996. If you actually look at this image in blown up form, you'll see a lot of things that might look like disturbed or interacting galaxies, along with the smallish dots that are far away. So the interacting things are not only local, but they're at great distances as well. And I made this up for another talk, but I thought I would throw it in. Why do we really care about luminous infrared galaxies, the thing that I study? It's because they rule the universe at high redshift. If you thought the mergers are exotic that you see today, they were 1,000 times more numerous when the universe was only 20% of its current age. So a lot of the merging and stuff that we're seeing now locally has been going on at a very rapid rate in the past. Matter of fact, all the ellipticals that we see now have been built up this way through mergers of spirals. So I just thought it cute that if you actually look in the Hubble Deep Field, you could see these things. And matter of fact, in my field, when we actually looked at the Hubble Deep Field, what we found was that this little red object right here, this is so far away, actually, that you can't see what the heck is going on here. If you add up all the optical luminosity that's coming out of about 2,000 points that you find in here, and this is a 2D image, but of course, if you knew the redshift, you could get the distance and make this into a 3D image. So the fainter things are much farther away. The brighter things and bigger things are usually closer. If you added up all the optical light, okay, that would not equal the infrared emission that's coming out of that little red dot. So when two galaxies, and we now know that that's likely to be a major merger of something like the Andromeda and the Milky Way occurring at a time when the universe was only 30% of its current age. And what happens when all that material dust gets swept into the center, the black hole starts fueling up, stars made like crazy, is that a galaxy can increase its total luminosity by a factor of about 3 to 5,000 maximal. And that's exactly what's going on here. It outshines in the infrared all of these galaxies in the optical. So it's a quite exciting phase that we're discovering. So here's that old picture of our local group 5 billion years from now, 4 billion. You look up at the night sky, you might see Andromeda a little closer to you. I mean, I had to produce this in a 1 hour stretch in the evening before a conference in Napa Valley. Turns out the theorists that know how to hold conferences, they rented out a vineyard for a week, and we had a show and tell in Napa at the Silverado Resort. And so I gave an after-dinner talk, and someone said, well, what would the night sky look like? I said, 4 billion years, Andromeda would be a lot bigger. You'd look up, and you actually would see it, like the moon or something. You know, it would be there, spiral. And I really do only have, let me see if I can click this, if it'll go. No, maybe not. I can try here. Ah, yes. So I'm just running through this again. Imagine this to be Andromeda and the Milky Way. The sun is probably out in one of these arms now. Hopefully it's going to fall back in. Hopefully. The disks, a bridge in between. This is all just gravity and stars being pulled out. And now they're going to plunge back in again. And this is 200 million year time steps. So if you look up at the night sky at any one time, your constellations are going to be moving around and shifted. Well, depending on where you are.
Wouldn't
But
the black holes consume you if it goes right over you?
well, hopefully we have enough orbital angular momentum never to plunge through the center like that. But that's a good question. You'd have to get pretty close to the black hole to actually get eaten by it. That's why you need that gas to collide and really sift down into the center where it gets, huh? Ooh. Wow, yes. That's what you're worried about, is that we end up out there. I agree with you. Oh, I don't want to do that again.
What would be so bad?
Well, but hold on. 5 billion years from now, we should have merged, and my guess is you might look up and see two Milky Way disks. Although I think most of the gas and dust by this time will have been swept into the center region, so it may not actually be two disks anymore, but I just thought that was cute. And then, of course, sorry, let me see if I can back up to the final slide, and I will end. What will happen, though, after we go through the luminous infrared phase, is the quasar that's being built up in the center should actually look something like that, if you could view it close up. Thank you. Yeah. And I'm open to names. I don't know what you want to call our new home, but that is what's going to happen to us and our home, the Milky Way. And at the same time, so if you thought you were having a bad day when the sun becomes a red giant, just realize that you're being incorporated into another galactic system as well. Yeah. And this whole thing is if you could actually peer up you would actually see, probably as the dust is blown out, you would actually see a quasar, which is shining at a luminosity 100 times that of the Milky Way. But it's fairly far away, so it would be as bright as the moon, but a very small dot. And I don't know whether you could see any of the quasars are spinning usually, and they shoot out, gas and dust or energy along a perpendicular axis to the accretion or the material that's still rotating around them. I don't know whether you could see any of that scattered light, whether you would see beams of that jetting out. but it would be neat. I've already had plenty of questions. You're an intelligent audience, so I need to come back. I mean, yes.
You said when it merges,
yeah.
would the two black holes like merge with each other and get bigger as well then?
The actual merger of the pre-existing black holes, right? We have a 3 million solar mass black hole now in our own galaxy. We have presumably a 3 million solar mass or something close to that in Andromeda. They behave gravitationally, so as the two galaxies, merge, eventually the centers of those two galaxies find each other, and eventually those black... Now, the theorists thought, were hung up and said black holes will never merge because they'll just go into an orbit around each other and get stuck. And the minute we said, well, look, there's gas in these merging spirals, the gas will sink to the center, and it will act to slow down that orbital angular momentum, and then they finally got it. And so, yes, eventually those black holes will merge. But that event only increases a 3 million solar mass black hole to a 6 million solar mass black hole. That event is quite powerful because it's a very quick thing, and it will send out strong gravity waves. But the actual building of the black hole by another factor of 100 occurs from the accretion of gas and dust that was swept in from the two disks. And it's food, it's fuel. It just sits there, but it feels the gravitational potential of that 6 million now solar mass black hole, and that stuff just rains down on top of the black hole. And I think if you accrete as little as a solar mass per year, you can outshine the Milky Way by a factor of 100. Because the nuclear fuel, hydrogen makes helium. That's not a very, that's a bomb, but that's not a very efficient process. Just take E equals mc squared and get a tenth of that out every time a particle falls in to a black hole, and that's 100 times more than the nuclear reaction of hydrogen burning to helium. And so that's where the black hole actually grows in mass. I think we call it an E-folding time. It increases its mass by a factor of 3 every 10 to the 8th years. So in 10 to the 9 years, it would grow by, what is that, 2.72 to the 10th power. You figure it out. It's a factor of a few hundred. So it goes from 10 to the near 10 to the 7th to near 10 to the 9. I mean, that's the way we do, you think sort of order of magnitude type stuff, but yeah. So billion solar mass.
Named appropriately, Andromeda Mesmer.
Oh, wow. Okay.
Assuming there was life in the solar system, how much in the way of X-rays would be coming in our direction, enough to threaten life, assuming any was left?
Well, you're right about not being any left of life because we'd be inside the sun, unless we'd found a way to migrate outward to the outer planets. Maybe we'd be okay, or whatever our ancestors were 5 billion years from now. But so you're asking this beast in the galactic center, this new thing that's built up in the galactic center, would it kill us from its X-rays? I know Alex Filipenko has a TV program on that where he talks about gamma ray bursts and having and he's sort of right, although he's being dramatic. He knows what he has to do is that there's beams of stuff that come out. It's directed energy usually that comes out of the black holes. He's got to have that beam coming directly at you. It's a very small opening angle. So the answer is probably not. It wouldn't do much to us. It just looked neat in the sky. Yeah. We have other problems due to the sun becoming a red giant. But I venture to say that most of you probably hadn't thought of this aspect of your life 5 billion years down the road. You're mostly focused on the sun and what it's doing and how it remains stable over a period of time before it goes nuts. And thankfully, that stable period is 10 billion years approximately, and we're halfway through that. Just I wanted to give you something to think about 5 billion years down the road.
Would it be that bad? Would it be that really that bad to be kind of on the outside of this? Because with the collision, that would have more material flying through our universe or through our solar system, right? could get hit? I mean, what would happen if we're far out?
You know, when that merger is occurring and gas and dust is getting swept into the center and stars are getting rearranged, there's not really much that changes in the solar neighborhood. I mean, the sun, you know, you're looking at the time steps that go, that's 100 million years that goes into one of the rotations, you know, that's going on while those galaxies are doing this. When I say rotation, I meant when they pass each other once and come back. That's sort of like one rotation period of a galaxy going around 200 million years, something like that. Okay? The sun is sitting there in one of these pinwheels, getting jostled a little bit, but the jostling doesn't occur like that. It occurs over millions and millions of years. And so the sun, instead of going off in that direction in the Milky Way, taking its planets with it, is maybe going off in that direction. You don't know the difference until you wake up 100 million years from now and look up, and the constellations in the sky are different because all the stars have been sort of moved in different directions. I don't know how else better to explain it than that. Yeah. Yes.
These molecular clouds.
Yes. Yes.
As this collision start to occur when Andromeda is coming to the Milky Way.
Yeah.
Does the UV fields start to affect it again in any way?
No, not much. No, because the molecular, that's a great question. The molecular clouds, in terms of remaining molecular, for example, and in other words, does this merger, does it somehow disrupt the molecular clouds and turn them into atomic clouds again so they can't form stars? Very good question. The answer is no. Because in order to really disrupt the molecular cloud, you've got to have something right inside it or right very near it that's all of a sudden become a very massive star and turns on and emits a lot of UV radiation, and that can blow and go supernova. And that's actually really what blows clouds apart. It's the supernova explosions that occur from the massive stars that are formed inside the cloud. But even supernovae, that's the neat thing, you're going off into my thesis. We had a 10-year, 20-year running debate that's only been settled very recently on the lifetimes of giant molecular clouds. And why do you get giant molecular clouds in the first place? Well, you get enough gas and dust, it gravitates, and you get these balls of stuff that keep getting bigger and bigger as they collide until something, makes a back pressure, and that's the stars that form inside them. And stars form with a mass spectrum, low mass, high mass. Well, the high mass ones evolve very quickly, 1 million years, and then explode as supernovae and give off, 100 times as much energy as the sun. And it turns out that you can have 50 supernovae going off inside the Orion giant molecular cloud and not blow it completely apart. And that's what I figured out a long time ago. And so I argued strenuously that if a cloud got big enough to 1 million solar masses, it could hold itself together over many epochs of supernova explosions, which would eventually, blow it apart and fragment it, but never really completely destroy it. Now that's all happening locally. So when two galaxies are colliding, you're not adding very much extra UV radiation from the...
You were saying that the gas clouds would coalesce.
Well, okay. I was talking about the early phases of that thing. If you actually looked at that gas, it's only when the things finally merge, in that final stage, that gas really starts to move in towards the center. Yeah.
So then presumably in the final elliptical phase,
yes,
there is going to be much less star formation going on.
That's right. Of new stars out in the gas. Yeah, the disk becomes basically red and dead, as they say. Old, red and dead. But that phase just before that occurs, when you've made the elliptical, that's this luminous infrared phase of the very active center and the buildup. And then what happens there is when that black hole really turns on, you get a massive explosion.
You keep saying this, and I keep looking at the cartwheel, and
Yeah.
I can't help it.
And the cartwheel has nothing to do with that. The cartwheel was a face-on and a edge-on galaxy colliding. And the edge-on just goes right through the face-on, and it splatters the face-on into a ring. Yeah. Yeah. So that's what the modelers get that out by just doing different geometries, and they can create all the fancy pictures that you see in the ARP Atlas. Yeah.
So, to get the geometry correct, you say in about 2 billion years we're
I think that's about right. Is it 300 kilometers per second that we're approaching each other at? And a kilometer per second is a parsec per million years. So in a billion years, a kilometer per second, so 300 parsecs per million years. So in 100 million years, you would go, yeah, that's trying to do it in my head, but a few 100 million years, I think we should be pretty much passing by each other. Sorry? I don't know. That's a good question. My feeling is that the outer parts will certainly touch. Yeah. I don't think we're plunging two nuclei directly towards each other because we have orbital angular momentum in this local group as well. So yeah. Yeah, but they feel it. But the outer parts, it's like a well, it's like a tide. It's called a tidal force, right? I mean, you have the outer parts feel the approach first, and they respond the quickest, and they get ripped out.
Well, what does touch really mean?
Touch does not mean stars physically touching, but the actual size of the disk overlaps with the other disk. Yeah, in space.
Some of them do collide.
Not the stars, no. They're just pinpoints. I mean, the stellar density. I think the way I think if we shrank I had a scale model of galaxy. If you shrink it down such that the galaxy is the size of the island of Maui, the 20 kiloparsecs is the size of the island of Maui. Stars would be 1 meter apart, and the size of your solar system would be the size of a pinhead. Think about that. So this room would have stars every meter, and the size of your solar system from the sun out to Pluto's orbit would be the size of a pinhead. Okay, so as far as we've been able to communicate or navigate is the Voyager spacecraft. It's gone the size of a pinhead. You know, we haven't gotten to the nearest star yet. And so you take a room full of these pinheads and pass one room through another room, the likelihood of collisions is 0 between those little pinheads. That's the way to think of it. It's the way to think of it. Huh? No, but I mean, you really to get the point, you have to scale it down to a scale model, and I've been teaching this enough I've heard these questions, but that's the way to think of it. But they feel each other, and they can redistribute themselves.
That's what I wondered. I mean, the gravitational force is passing. I mean,
yes.
Going to change
Yes.
just the whole
Yes.
motion of everything.
Yes.
So we've been in orbit around Andromeda for a second.
You mean the local group has? Yeah, the local.
Orbit around the mutual center of gravity.
Right.
13 billion years plus. Now.
That's a good point. That's when did structure form? That's right. Maybe 10% after the age of the universe, the beginning of the universe, you started to get gravity pulling things back together. We live in an overdensity region, right? That's what we live in, this little group held together by gravity. Now we know dark energy in between the groups is pushing things apart. Dark matter helps pull us together a little bit. But that whole structure was set up, you're right, probably 12 billion years ago. And so we've been orbiting around as this group over that period of time.
And this coming up is going to be the first hit.
It's going to be the final hit of the two leftover big things. I don't know whether we started out with 2 Andromeda and the Milky Way, but eventually we got to that point with all the little satellites still left. My feeling is we'll eat our satellites before we actually merge the 2 objects, but in the end we're going to be left with one big elliptical.
Do we know the trajectories?
Yeah, I mean that can sort of be mapped out.
So when they both,
Yeah.
when
Yeah.
we're left with this elliptical,
Yeah.
is it, well, how is it that size compared to other galaxies?
Well, our local group will have merged into one thing, one big elliptical, sort of twice the mass of our.
Bigger than other galaxies, or smaller, or just equal?
Well, already in terms of spiral galaxies, we're sort of on the large end of spirals. When we merge with Andromeda, we'll be sort of twice our mass and an elliptical, and that'll be sort of like largish elliptical. Yeah, so you can feel good about that. You can carry your weight. There will still be galaxies bigger than you, but and we can look out and see other groups that are going through the process that we're hypothesizing for our own galaxy. We can see end stages. We can see not everything starts out with just 24 galaxies. There's the Virgo cluster, which has 1,000 galaxies. There's the Coma cluster, which has 10,000 galaxies. Imagine what happens when all those things merge. Yeah.
Another question. It's from Nebadan Izumi.
Oh.
He's the guy in the blue on the far lower left. He's also head of the OpenSim grid. Yeah. It's a privilege having him here.
Yeah.
He wants to know if the galaxies could exchange stars.
Yes.
During the first pass.
Ah, yes. In the outer parts, yes. Quite, yes.
Okay, so they can
yes.
Across.
Yeah.
Cool.
Yeah. Yeah, they can, yes.
Are your slides going to be available anywhere?
I could put it up on a website if you want, sure.
And this video, of course, is available.
No, but if JD tells me, I'll put it on a website and you can advertise it, download it if you want. It's not copyrighted or anything. I've actually given it out before. I've shown it in China, and I've shown it in Germany. I've shown it in Italy. I've shown it in Chile, and it's been picked up various places. So I feel comfortable letting it go out if it hasn't already. But no, seriously, if you keep
just put it on the
if you keep archives that
yeah,
sure. Do you have a web page? Maybe on your announcement web page, you could say click here and download.
Yeah.
Now it's 20 megabytes, so I'd have to package it up such that the movies were in it as well. But you can, with high-speed stuff, it's easy to download. Uh-huh. Anyway, I can put it all there with the movies. That's a great. I will do that. I will do that. Yeah. Okay. Yeah.
If our solar system does end up getting shot out, what would happen to us? Would we just keep going on forever?
We'd be a free-floating sun. There's a hypothesis that there's many free-floating stars in between the galaxies. As a matter of fact, when people were looking for dark matter, there was a thought that there were low-mass stars or other stars that were just pervasive throughout the intergalactic medium, maybe left over from being ripped off of galaxies. I don't think that that's the case, but it could be. Huh? Well, life would be determined by our sun, not by the other star. You don't get any energy from Alpha Centauri, but very little at least. So our sun could be free floating. That doesn't matter. What matters is its evolution and becoming a red giant and then eventually a white dwarf and then dying off. Yeah.
In this simulation, is this modeled after the supposed way Andromeda and the Milky Way merge? Has anybody done any simulations where maybe the galaxies come in together, or
you mean
back together? Is it just the edge-on going through a face-on galaxy is the simulation?
You're asking me whether I know the exact orbits of Andromeda and the Milky Way and how they're going to...
Simulations other than the one you showed.
Oh, they've run millions, billions of simulations. Yes, that's the whole... Yeah, matter of fact, in China, next week we're going to Taiwan. We're holding every 5 years or 10 years, it seems, we finally get around to holding a conference to talk about nothing but mergers. And so this will be the first conference in the last decade devoted just to that. And one of the things Barnes is presenting is he spent the last 5 years of his life, he's too detailed for me, but it's great when he does something. He's got something called Identikit, and you can actually plug in as much as you know about two galaxies. And what really counts, of course, is their orbital trajectories and then how massive they are. And then he can let it run. And then he will predict the byproduct or the outcome. And so that's how he's able to go from one of these art pictures down here, and he can actually tell you what the orbits were, how far, whether they were, exactly. And it's a pretty good deal. He can actually, we think he can actually get the right answer. But,
Solar trajectories were predestined a long time ago.
Huh?
Our true trajectories were predestined.
Well, it's a byproduct of how the whole local cluster, this little, it's not even a big cluster, it's called a poor group. That's what we live in. Yeah, it's pretty sad. You know, we're a typical star on the outskirts of a typical galaxy, sort of, and we live in a poor group of galaxies. Sort of makes you feel inconsequential, but
here we are.
Yeah, it's fine with me. Yeah. Okay?
Okay.
Thank you.